A young planet scorches at 460 degrees Fahrenheit. Its atmosphere swirls with salt, thick clouds of sodium and potassium chloride drifting through an alien sky. 57 light-years away, a space telescope just detected them. What it found is rewriting what we know about how planets form. The world carries a catalog name, GJ504b. It orbits a star in Virgo, one of thousands of exoplanet discoveries scattered across the sky. But this one is different in ways that matter. It's a gas giant, roughly 2 times Jupiter's mass, still young, about 200 million years old. Young, on a cosmic scale, means it's still hot. It's still radiating energy from its birth, still cooling in the void of space. Every star that gets cataloged has neighbors. Most planets we've found are ancient, settled into stable orbits around stars they've circled for billions of years. We find them indirectly. We watch them cross in front of their stars and notice the dimming. Or we measure the tiny wobble their gravity creates in the star's motion. These methods are clever but distant. They tell us a planet exists. They don't show us what it looks like. GJ504b is one of the exceptions. Astronomers didn't infer its existence, they saw it. They directly imaged it, a feat so difficult that fewer than 30 exoplanets have ever been photographed this way. Direct imaging requires 2 things to align perfectly. The planet must be young, still glowing with residual heat. And it must be far from its star, far enough that the star's blinding light doesn't wash out the planet's faint infrared glow. GJ504b orbits at a distance where both conditions hold. It's far enough. It's hot enough, and so it became visible. Once astronomers directly image a planet, studying it in detail becomes possible. They can point powerful telescopes at the world itself, rather than trying to infer its properties from the star's behavior. When the James Webb Space Telescope acquired GJ504b, the discovery it made was one few had predicted would come so soon. JWST is a master of infrared spectroscopy. Light from the planet passes through its sensors and breaks down into a spectrum, a rainbow of infrared wavelengths. Each chemical element leaves an imprint, a signature that says, carbon dioxide is here, water is here, methane is here. Salt leaves its own unmistakable signature. Sodium and potassium chloride have specific absorption features in the infrared. When JWST analyzed GJ504b's light, it revealed signatures unmistakable, not faint, not ambiguous, but clear and quantifiable. The salt clouds were not a detection on the edge of uncertainty. Scientists could measure how much salt was present, at what altitude the clouds formed, and how they spread across the planet's atmosphere. This level of detail had never come before from a directly imaged exoplanet. It was a proof of concept. It was proof that JWST could not just confirm that an exoplanet exists, but could interrogate its weather, its chemistry, its atmospheric structure in real time. Why does a salt cloud matter? Because it's a window into planetary birth. Every world's atmosphere tells the story of its age. Young planets are different from old ones. Their atmospheres haven't settled. Chemistry is still active. Molecules form and break apart. Clouds condense in ways shaped by the planet's temperature, pressure, and composition. At 510 Kelvin, hotter than any natural place on Earth's surface, salt doesn't behave as it would on a cooler world. It doesn't rain down. It doesn't freeze. It crystallizes into particles suspended in the atmosphere, creating clouds of white crystals in an alien sky. For 3 decades, astronomers have pieced together exoplanet atmospheres like a jigsaw puzzle. They found methane on one world, water on another, carbon dioxide elsewhere. But those were mostly old, cold planets scientists studied indirectly, their atmospheres inferred from the starlight passing through them. GJ504b is different. It's a young world. Its atmosphere is still forming. Looking at it is like looking at a planetary embryo. And what we see challenges our models. Planet formation theories predict certain atmospheric compositions at certain ages. GJ504b's salt clouds suggest the reality is more complex, more dynamic than those models account for. Young planets aren't simple. They're chemical laboratories. They're systems where processes we barely understand are unfolding. JWST just gave us a front-row seat to that process. And once you've seen one planetary nursery in detail, you realize how much we've been missing about the early stages of planetary development. GJ504b answered one question. What does a young, directly imaged exoplanet's atmosphere look like? But it opened many more. How many other young planets are out there, waiting to be imaged? What other atmospheric compositions will JWST find? Chlorides we expected, or chemical signatures we haven't predicted? Most importantly, what will we learn about planetary formation when we can study these worlds while they're young, while they're still transforming? The salt clouds of GJ504b are not the end of this story, they're a beginning. Every newly imaged exoplanet, every spectral analysis, every detected chemical signature adds another piece to the puzzle of how worlds are born. We're entering an era where we don't just know that distant planets exist. We're beginning to see what they look like, what they're made of, and what secrets they hold. The universe is far more detailed, far more various than we could observe from Earth just a few years ago, and it's only getting clearer.